In our last presentation, we reviewed three properties of the Laplace transform: the linearity, time shift, and frequency shift properties. In this presentation, we'll discuss two more: the time differentiation and the time integration properties. These properties will be among the most important that we will discuss in this class. First, let's tackle the time differentiation property. It says as follows: if the Laplace transform of a signal x of t is labeled x of s, then we can find the Laplace transform of the derivative of x of t simply by multiplying x of s by s and subtracting the initial condition of x at time 0 minus. Mathematically, we write Laplace transform of dx dt is s x of s minus x at time 0 minus. An example of this property is given below. Let's suppose we have the position of an object and it's given by x of t equals 3 e to the minus t u of t. We want to find the Laplace transform of the velocity signal. So the velocity is the time derivative of the position. First, we'll find the Laplace transform of x of t. And go into our Laplace transform table, we'll find it is 3 over s plus 1. We'll note the value of x at time 0 minus is 0, since there's a discontinuity in x at time 0. So, using the time differentiation property, we have the following. The velocity, which we'll label v of s, is the Laplace transform of dx dt, which will be s times x of s minus x at time 0 minus. X of s is 3 over s plus 1, so this is s times 3 over s plus 1 minus 0. So we find as an answer v of s is equal to 3s over s plus 1. Admittedly, having a discontinuity in position at time 0 is not physically realistic. Now to finish this example, we'll take the inverse Laplace transform. So v of s is 3s over s plus 1, which we can expand to 3 minus 3 over s plus 1. We can then take the inverse Laplace transform of this, and we find v of t is 3 times the Dirac delta minus 3e to the minus t u of t, which we graph here. You notice there's a Dirac delta of strength 3 at time 0. This is what's necessary in terms of velocity to cause the position to jump discontinuously at that time. We'll now tackle a slight variation on this example that gives a considerably different result. Suppose now the position is given as follows: x of t is 3e to the minus t for t greater than 0 minus. So this is not the same function as before, which was x of t is 3e to the minus t u of t. We're specifying here the position just for time 0 minus and greater. And x at time 0 minus in this example is now 3, not 0. We'll now use the time differentiation property again, but now with this signal. We find v of s is s times x of s minus the initial condition. That will be s times 3 over s plus 1 minus the initial condition, which is 3. Performing the algebra, we find v of s is minus 3 over s plus 1. So you see, this is a very different result than we found before. If we inverse Laplace transform this, we'll find v of t is minus 3 e to the minus t for t greater than 0 minus. And you'll note now there's no Dirac delta in v of t, as there was before. This is because there's no discontinuity in position between time 0 minus and time 0 plus. You may find it confusing that in these examples we got different answers, significantly different answers. You may think that these two signals are the same, but it's not surprising actually. The two signals that we looked at are different. The first one has a discontinuity at time 0, and the second one does not. And therefore, the velocity that we find will be different in the two cases. So this points out the importance of thinking about initial conditions carefully when we're tackling problems using the differentiation property. Here is one guideline for considering this issue. If x of t is an external signal, then x at time 0 minus will be 0, since the Laplace transform will require x of t equals 0 for t less than 0, since it has to be a causal signal to have a Laplace transform that is unilateral. If x of t is an internal signal, then x of 0 minus is just the initial condition on that state. It does not necessarily have to be 0. This second case will be very important for the analysis of the system's zero input response. The time differentiation property can be extended to second, third, and higher order derivatives of signals. Let's look at the second order case first. The Laplace transform of the second derivative of x is equal to s squared times x of s minus s times x at time 0 minus x dot at time 0 minus. For the general case, we have the following result. Laplace transform of the nth derivative of x with respect to time is equal to s to the n times x of s minus a summation of powers of s times derivatives of x evaluated at time 0 minus. The derivative here is given by the notation x to the parentheses k minus 1 that indicates the k minus 1th derivative of x, a time domain signal, evaluated at time 0 minus. This result for the general case is easy to prove. By induction, we just need to apply the first order result repeatedly, and we'll find that we achieve this. This time differentiation property will be very important to the analysis of differential equations, because it allows us to transform differential equations into algebraic equations once they've been put in the frequency domain. Let's look at an example. We'll consider a mass on a spring. The output signal is the displacement of the mass y. There is no input signal, so this is a zero input case. This system is governed by the differential equation my double dot plus ky equals 0. And we'll look at the problem with initial conditions y at time 0 minus is 3 and y dot at time 0 minus is negative 2. So this has an initial condition on both position and on velocity. We'll Laplace transform the differential equation. We take the Laplace transform of my double dot plus the Laplace transform of ky equals the Laplace transform of 0. Well, the Laplace transform of 0 is obviously 0. And on the left-hand side, we've used the linearity property of the Laplace transform to break it up into terms. We can pull the m and the k out of the Laplace transforms, and we'll get the second line, m Laplace transform of y double dot plus k times Laplace transform of y equals 0. We'll label the Laplace transform of y of t as capital Y of s, and then the Laplace transform of y double dot by our result for the second derivative will be s squared times y of s minus s times y at time 0 minus y dot at time 0 minus. Substituting our values for the initial conditions, which are 3 for the position at time 0 minus and -2 for the velocity at time 0 minus, we achieve the first line on this slide. The Laplace transform of y double dot is s squared times y of s minus 3s plus 2. We'll now substitute that back into our equation, our differential equation after Laplace transforming, and we'll have m times the quantity s squared y of s minus 3s plus 2. Of course, that's the Laplace transform of y double dot, plus k times y of s is equal to 0. Now this is the differential equation with now the initial conditions also present after Laplace transforming. And you note it's now an algebraic equation. We can do algebra on this. We can move terms around. There is no differentials anymore. So, performing algebra, we'll group the terms that are multiplying y of s. And we'll get ms squared plus k times y of s. And then we'll gather all the other terms on the right-hand side. That's 3ms minus 2m. We'll then divide through by ms squared plus k to find y of s. So y of s is m times 3s minus 2 over ms squared plus k. You see, we've been able to do algebra to find y of s, the signal. Now our last step is to inverse Laplace transform y of s to find y of t. And for that, we simply go to our Laplace transform table. I'll leave that step to you. I hope this example shows you how useful the Laplace transform is for tackling differential equations with initial conditions. You see, it transforms them into algebraic equations, which then allow us to solve for the variable of interest. You probably have suspected that if there's a differentiation property for Laplace transform, there must be an integration property as well. And there is. So let's review that here. If the Laplace transform of some signal x of t we call x of s, then the Laplace transform of the integral of x of tau d tau is equal to 1 over s times x of s. Now you should see a trend here. When we had the Laplace transform of a derivative of a signal, we could find that by multiplying the Laplace transform of the signal by s. And when we want the Laplace transform of an integral of a signal, we take the Laplace transform of the signal and multiply by 1 over s. So multiplying by s is like taking a derivative, and dividing by s is like taking an integral. Now I know some students are still struggling with trying to understand what it physically means to be the integral of a signal. When we say the integral from 0 minus to t of x of tau d tau, what does that mean? Now if we think of a graph of the x signal, then the integral from 0 minus to t of x of tau d tau is just the area underneath the curve between 0 minus and t. You can think of it as the accumulation of x over the period from 0 minus to t. This example should make it more clear. We'll look at the water bucket problem again. So we have water flowing into an empty bucket. The flow rate is given by the signal x of t, and that's in liters per second. The volume of water in the bucket is given by y. We start with an empty bucket at time 0. Then the volume at time t, that is y of t, is the integral from 0 minus to t of x of tau d tau. We're simply accumulating all the flow rate to find the volume. In terms of the frequency domain, this is given as y of s is equal to 1 over s times x of s. That is, y is the integral of the flow rate. So whenever you see a multiplication by 1 over s, you should immediately think of this integration or accumulation of the x signal. This integration is actually a system. We have y of s equals 1 over s times x of s. We think of x of s as the input and y of s as the output. And you note that these two signals are related, and they're related through the system. So we think of this as an integrator system. Flow rate going in and volume coming out, and the relationship given by 1 over s in the frequency domain. Integrator systems are extremely common in engineering. There are many things which are the integral of an input. For example, position is the integral of velocity, and velocity is the integral of acceleration. Charge is the integral of electrical current. I had mentioned that velocity was the integral of acceleration, and position was the integral of velocity. So that means the relationship between acceleration and position is one of a double integrator. We can represent this in diagrams as follows. We have x of t, or alternatively x of s, going into a system which integrates it. That system is given by 1 over s in the frequency domain. Out comes v of t, or alternatively v of s, which goes into another integrator, shown by 1 over s. And then out of that comes the position y of t, or y of s. Now, we can call the signal x of t, or we can call it x of s. It's the same signal. These are just two different representations of the signal. So this diagram shows the relationship between signals. And so when I write 1 over s, I'm indicating the integrator relationship. Now, if I don't wish to show my velocity signal, I can combine the two 1 over s's and write 1 over s squared. That indicates the relationship between acceleration and position. So I can show acceleration as the input, x of s, and position as the output, y of s, with the system in between, 1 over s squared, indicating a double integral.
Look, guys, look! Is that what I think it is? No, it can't be. It is! It's the fabled Mech 205, where all wisdom of the universe is imparted! Come on, guys, let's go! Hello? Is anybody here?
Boss? Hello?
Come on, guys, let's go inside! Oh, what's that sound? I'm scared! What is it?
Oh my, that was embarrassing. I am Laplace, the great and powerful. Who are you?
We're mech system students, but you're just a floating head.
Fine then, leave my presence. No wisdom for you.
No, please! You must show us the Laplace transform!
Very well then, brace yourselves. This may be a bit overwhelming. It's a knowledge so profound, it has led many to sheer madness. Behold, the Laplace transform, in all of its majestic glory.
What? That's it? That's the magical Laplace transform? How in the world is that helpful to me?
O ye of little faith, tell me, what art thou studying now?
Mechanical systems, H of T, that kind of stuff.
Very well then, riddle me this. How would you find the impulse response of the following differential equation?
Easy. Simplified impulse matching method.
Interesting choice. Let us give your method a go then. Let's see. Let's write it in a slightly different format. You know, your Q of D and P of D format. Because M is less than N, B0 is 0. Therefore H of T is P of D times Y of T times U of T. Next, you must solve the characteristic equation to find the characteristic modes and solve for their coefficients. Now, multiply the equation you just solved for times d plus 1. Simplify through algebra and you have h of t. Quite a tedious process, wouldn't you say?
Yes. Tell us, great Laplace, isn't there a better way?
Oh, yes, there is a much better way. Haha, haha. Let us apply the Laplace transform you so quickly discredited. Look here, let's take our differential equation and take the Laplace transform to enter the frequency domain. Here we shall assume zero initial conditions, and make sure to use the rules outlined in Untitled Chapter 4. Once in the frequency domain, divide P of d by Q of d, which is something very special called the transfer function. Now, just partial fraction expand your transfer function to simplify. Then, take the inverse Laplace, using the transform table, and voila, you're back in the time domain again, with your desired impulse response h of t. So, what think you now of the Laplace transform?
Oh my goodness, it's so beautiful. It takes differential equations and turns them into algebraic equations. My life will never be the same.
Ah yes, that's true, and there is so much more you can, and will do with it. Ha, ha, ha 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 ha.
Cause we gon' make a movie, it's gon' be a 3D, a 3D,